So Shuran is an assistant professor at Columbia University. She's been doing some really cool work lately in perception and manipulation. You've probably seen some of the work here, especially with the robot and cutting the avocados. Winning awards constantly left and right, it feels like. So she's has some really cool language work, especially coming from a perception direction. So yeah, please join me in welcoming her.
Cool. Okay, so hello everyone. Good afternoon, and great that you're still awake. So today I'm going to talk about hierarchical representations for language-based reasoning and in the context of robotics. But I think what I'm going to talk about is really motivated by this question that how to ground those really powerful LLMs, large language models, onto the physical world so that it can be more useful for our robotic systems. So before I start, I want to just quickly touch base on this concept of using language as a cognitive tool, right? So I think long before the existence of large language model, there is already a lot of theory in cognitive development that hypothesize that although language is initially learned through and for communication, it is later internalized and then used as a cognitive tool to help us organize our thoughts, right? So in another word, our ability to use language actually become a very critical part of our reasoning and planning capability. And then we all know that when LLM become a thing, there's actually also provide us a very concrete way to kind of implement this idea or validate this hypothesis. Right? So recently you can see like so many papers in robotics that try to capitalize this idea of using large language models for task planning or reasoning. And then I want to say that one of the most impressive part about all these systems is their amazing ability in generalizing to new tasks or their flexibility in handling new tasks, right? As long as your task can be described by some kind of objects, a combination of some objects that can be detected by an object detector, or some action that come from a predefined library. So as a result, this kind of object detector or predefined action library really becomes the link that kind of connects our cognitive tool, like the large language model, and our physical world. Oftentimes it's messy and unstructured, right? But I think, unfortunately, this kind of object detector and predefined action library is also kind of become the bottleneck for a lot of those robotic systems nowadays. And in particular, for example, if your object detector or VLMs are not expressive enough to describe certain object states, then the robot may just lose some very critical, important information to provide to perform reasoning. So, for example, if your LLM if your object detector can detect egg but cannot detect the states whether it's a good egg or broken egg, then it cannot really like reason or plan on top of that. And similarly, I would say that still today it's still very hard to kind of allows our robots to acquire new skill sets actually outside existing predefined libraries. So there's a lot of work on that, but I think that is still quite a challenge in today's robotic system, especially LLM-based robot systems. So as a robotics or like computer vision researcher, I'm actually quite happy about this observation because that means that I will still have my job for a while, like to solve this grounding problem. So today I'm going to talk about two of our very recent work that kind of focus on these questions of how to ground those LLMs into our physical world. In particular, how to ground it through robust perception, like especially multi-modal, multi-sensory perception, and then also low-level robot actions. So first, I'm going to talk about our work on how to ground LLMs in perception. In other words, how to kind of describe what's going on in the physical world in the form of natural language so that we can later use LLM to reason about it. So this is a work done by my student Ziyi and Arpit, and the title of the work is called Reflect, Summarizing Robust Experience for Failure Explanation and Correction. So we study this problem in the context of robot failure reasoning. I want the robot to reason about why they fail on certain tasks. So first, why we care about this task? I would say that With increasing demands or expectations of our wants our robot to do more and more complex tasks, we kind of need to admit that failure is just going to be inevitable, right? They're going to fail at some point. And then at the same time, I have to say that in order to identify the cause of failure in a robotic system is actually really tedious. It oftentimes involves reading hours and hours of robot logs, watching all the videos in order to identify which part it caused the ultimate failure. And I think today's self-driving car is actually a very good example for this problem, because given that we have so many cars running on the streets, collecting tons of data every day, in the end of the day, we still need some humans sitting in front of the computer to watch the video logs in order to kind of identify what went wrong and categorize the failures so that they can send to the engineering team to fix it. So that's really like highlights the bottlenecks of like failure reasoning is a real need. So the question we want to ask in this project is that can we develop algorithm that's able to kind of automatically detect and explain what went wrong in a robot execution? Right, so in particular, we're going to formulate this failure reasoning task as following. So the input of the system will be the robot's log data that includes their vision, whatever sensory data they have collected, and also their action plans, their executions. And then the output of the system will be a text format of explaining why the robot failed at this task, like the reason, and also localizing when the robot when this failure happened. And also later you can see that we can also, based on this reasoning, we can provide a replan so that the robot can correct this error afterwards. So that is the problem formulation, or like the definition for failure reasoning. And then the next question is that what does it take for a robot to have the capability to reason about failures, right? So I think here it's just, I think, three basic requirements for a robot to reason about failures. So first, they need to have the ability to able to summarize what happened, right? So basically, you looking at all the raw sensory input, summarizing what happened during the execution. And then second, they need to be able to reason about what went wrong by identifying the cause of failure. So this step actually oftentimes require quite a long horizon reasoning, because the cause of failure may not immediately lead to failure during the execution. Sometimes it's actually quite far apart. And then finally, they need to be able to reason about what to do, like kind of generating a plan to correct this failure and complete the task. So among all these three capabilities, I have to say that the last two actually can be directly helped or benefit from LLMs by leveraging its impressive abilities in doing like common sense reasoning. So I would say that the biggest remaining challenge is still on the first step. It's basically how to generate an informative text-based summary so that we can use the capabilities of LLM so that they can reason about the failures. So that's also what I'm going to talk about or focus on in this talk, which is the first step, how to generate the informative text-based summary. So what actually make a good or informative robot summary in particular for failure reasoning? Right? So we actually identify two very important properties. So first is that we realize that the summary actually better to be hierarchical. Means that this summary better provides different level of abstraction in order to support different levels of reasonings, especially because failures can have many different forms. Right? So for example, there are low-level execution failures and also high-level planning failures. And if you higher-level summary may help the system to directly identify or categorize the type of failure or quickly localize the general region or time of failure. While the more detailed summary, like low-level summary, will be able to provide details on the exact time and the spatial locations of the failure events, which is very useful for the later error correction step. And then another properties we realize that's important for the summary is that it needs to be multisensory. Means that it needs to be able to leverage all the possible sensory modalities for the robot to actually reason about failure. Because certain failure or like object state is just much easier to be identified through one type of sensory data than others. Right? So earlier we had this very nice discussions about how we can make use of like sound or audio input. I think this is actually a very good example. Right? So for example, if you want to tell whether a water is running, it's just so much easier to kind of detect this state through audio than through visual data. And similarly, if you think about robot failure, collisions is actually a very important and salient signal that is actually very easy to detect through sound, but maybe hard through vision alone. So that's the motivation why we want to use all the possible sensory inputs that the robot can collect to provide this robot summary. Okay, so motivated by that observation, we introduced or designed this hierarchical multi-sensory robot summary. So that has multiple abstraction levels, right? In the lowest level, we try to have a sensory input summary that try to summarize those unstructured multi-sensory data into a detailed text description. So in this step, for example, given an RGBD video observation, we'll first detect the task-relevant objects using open vocabulary object detector, and we try to identify their object state using existing VLMs. And then we also extract very important 3D spatial information by using the depth data. And then all this information will be stored into a 3D scene graph that can be converted back and forth through the scene graph structure and the text format. And then similarly, we're also gonna convert the audio data into a text description by using audio language model. Here we're using audio clip. So in the end, we have all the frames summarized in a text format with all the detailed information. And then in the next level, or the second level, we'll try to condense the information by selecting keyframes based on some kind of critical events. Right? So here the critical events can be detected through, for example, the changes in the scene graph, audio events, or robot events, for example, by the end of each subtask. So we'll select those keyframes and then provide a shorter and more informative summary on the second level. And then in the last level, we try to further summarize the information based on the robot's original plan, right? So here we're gonna use the robot's original execution plan, and then for each of the subtasks in the robot's original plan, we try to summarize by its subtask goal and also the final observation for this step. So a note here is that this level of summary actually loses a lot of information, but we found that it's actually very helpful for the system to quickly narrow down the type of failure and also the step of failure. And we still have the lower level summaries for us to actually extract the low level details for the robot to do correction. So with the hierarchical multi-sensory summary, we can then go on to do this failure explanation. So we basically designed a progressive failure explanation module that's trying to systematically curate the LLM to generate failure explanation. So this part, I think LLM is actually really doing the heavy lifting, and we're just kind of prompting it to get the correct explanation. So for example, we'll start with the high-level summary, like the sub-goal summary, and we'll go through the LLM to ask them whether this step is, or this sub-goal is satisfied. And then if any of those sub-goals is not satisfied, then we'll go down one level. It probably means that this execution is failed, right? So for example, you want to pick up the apple, but the apple is not in the gripper, then we know that this pickup action, the execution has issues. So then for those cases, we'll actually go down one level for the summary and then use the event-based summary up to that step to kind of generate explanations for this particular failure type. There's also cases that when all the subtask is actually past the verification, but still the final task is not successful. That's more likely caused by planning failure. Like for example, the robot maybe missed a step, or there's a wrong order of steps. As a result, maybe every step is correct, but the end goal is not achieved. So in that case, we will ask the LLM to reason about the robot's original plan, and then the final state observation, and ask them about what's wrong with the robot plan. So with the failure explanation, like highlighting the green text here, we can again ask the LLM to kind of generate a correction plan to fix their error. And in particular, we can map the generated correction plan into the executable functions in the environment to actually control the robot. So to evaluate this system, we actually need to create a new data set that we call the robot file data set that contains all sorts of, we can think about issues and failure types that a robot can encounter in their execution or planning. And then we use that data set for evaluation. So here is just a quick visualization or a look on what's contained in the data set. The data set actually contains both real world and the simulation environment. And I think it's quite important to kind of validate different part of the algorithm by using these two type of data, right? So in the real world, our data set is kind of like an offline data set that can be used to validate the perception modules, like the vision modules or the sound modules, how accurate they are for to handle real world noisy data. And then the simulation environment is much more useful for like doing systematic evaluation, and also importantly, like the evaluating the replan, because you can actually control the robot to correct this action and see whether they can finally finish the task. So here is just one particular example in this data set. Let's see what it plays. Okay, yeah, so actually this both video is trying to do the same task. Try to like cook a carrot, and then but they actually failed for different reasons, right? So in the first example, it actually failed to cook the carrot because it picked up the spoon instead of knife, so the carrot is not cut. And the second example, the robot failed because it drops the knife at a certain point, and therefore the robot, the carrot is not sliced. And then here, the text showing here is actually generated by the algorithm. So I want to quickly mention a few limitations because I feel it's such an interesting and important problem, but we are like just getting started. I think there are still many things we can do about failure reasoning and explanation. Right, so first, I have to say that the current performance of failure detection is still really bottlenecked by the perception modules, right? So both the audio and the visual module, that is the part actually causes the biggest issue that limits the capability or the accuracy. And the second is that we found that this hierarchical summary actually can be very useful for many other tasks, like analyzing the efficiency of the robot behavior or collaborating with humans, in addition to just providing helping for a failure summary or a failure explanation. And then the last is that I think our data set or the examples that we evaluated on is still quite limited, although we tried our best to think about all the possible failure cases. And then we really feel like it would be nice if area labs start to contribute their failure robot videos instead of just showing the successful cases. And I think if you're interested, and we can talk offline, and then we can share those like robot fail data set and try to grow that data set. I think that will be very useful as a benchmark. So that is the project about grounding in the perception, basically like summarizing what happened through the robot's visual and also audio inputs in order to kind of help them to reason about failures and also correct failures. And then in the next project, I'm gonna kind of switch the gear and talk about how we can actually ground those LLMs to the physical world through robots' physical actions, right? In particular, low-level manipulation skills. So here, this is a project in collaboration with Pete Florence and my student Hui Ha. And then in this project, we try to define this low-level manipulation skill as acquiring 6-off closed-loop behaviors with high rate control. Right? So that is our definition of low-level manipulation skill. And I think if you have worked with LLM-based robot system, you'll realize that is still quite a challenging problem. Like if you want to get a new skill that is without human demonstration or kind of other data source, is still very hard. So how are we gonna do that? So this project is called Scaling Up and Distill Down Language-Guided Robot Skill Acquisition. So as suggested by the title, there's 2 parts to this project. So first part is we're trying to scale up the data collection by using large language models and the simulation environment to generate those rich robot behaviors and acquire different type of low-level manipulation skills. And so here we're actually gonna leverage all the information we can, like for example, the state information in simulation and also LLMs and also like motion libraries to generate those low-level behaviors. And in the second part, we're gonna try to distill down those robot experience into a lightweight visual motor policy so that it can be directly deployed on a robot and using their raw sensory inputs. So in the first part, scaling up part, we basically doing something very similar to a lot of existing work. Given a task description in language, we use LLM to recursively break down the task, basically generating a high-level plan. So this part is actually very similar to like SECAN, CODA's policy, those line of work. But an important difference here is that we actually also allow the large language model to call or make use of those sampling-based utility functions. Right? So for example, graph samplers or motion samplers to generate the low-level action in order to actually solve the particular task. So here, this sampling-based utility functions actually is very important because it introduces certain randomness in the low-level execution to allow the robot to perform a little bit of exploration in the low-level manipulation strategy, so that it's actually able to kind of figure out what is the actual low-level grasp that will be successful. And at the same time, it's different from like RL, like just letting the robot to randomly explore on the whole action space. We use LLM to help to narrow down and break down the task so that the search space is more trackable and it's not too large, so that we can make the exploration more efficient. And then finally, we also can use LLM to actually generate a reward function, or just basically a simple check, a function to check whether each of the subtasks is successful. Right? So here is actually a function that generated by LLM by using the state information in the simulator to check each of the steps whether it is successful or not. So this reward function is very important because it helps the system to know whether they are successful finish a task, and if a particular task or subtask is not successful, it will continue to retry at that level with, before popping into a higher level. Right? So this kind of, we call it a verify and retry module. It's actually very important to really help the system to collect more successful cases without suffering from this like long horizon problem, because you can actually have a quick verifications on each of the steps. And also more importantly, this kind of retry behavior also introduce some very useful, robust recovery behavior. So the robot actually now have some experience of knowing how to fix their errors through like when they encounter failures. And those robust recovery behavior is useful for us to train the later policy downstream. So at this point, we basically has a very large collection of robot experience that is multitask and also labeled with densely labeled with language and also the robot actions. So, and then the next step is trying to distill down those robot experience into a visual motor policy that is conditioned on language and can be directly deployed on the robot. So here, the actual implementation, we use diffusion policy to learn from all this robot experience, and we train a visual motor policy that is language conditioned. So this step is actually very important, although you probably don't see this step in a lot of language-based robots. They typically just stopped, like once they generate plan a low-level action, they stopped there. But I would say that this distillation step is quite important because it can address a lot of the common limitations for LLM-based robot systems. So for example, it's by doing this distillation step, we allow the robot to kind of infer action directly from the raw sensory inputs like images, and without relying on some external object detectors or state estimators. Oops. I have a second point. Okay, yeah, and the second limitation it's able to address is that it allows the robot or the whole system to continuously improve its low-level skills with more and more experience without the need to actually fine-tune the large language model itself, right? Because it can directly train this distilled policy, and it doesn't really need to fine-tune the LLM itself, which is oftentimes a lot more expensive and not affordable. So in the end, we actually evaluate the system with a lot of different complex manipulation tasks that involve long horizon planning, common sense knowledge, tool use, and intuitive physics. And then our evaluation does show that with this framework, we are able to quite significantly improve based upon those LLM-based policies or robot systems. And also at the same time, the learned policy is able to inherit those robust retraining behaviors from its training data. So that is pretty encouraging. Okay, so to summarize, today I talked about two projects, and both is kind of thinking about this question of how to ground large language models in the physical world, but from two very different aspects, right? So one is grounding in perception, the other is grounding on the low-level robot actions. But if you look at these two projects at the same time, we'll realize that the hierarchical representation is actually quite important. And so for example, in the first project, we kind of see that using bottom-up summarization, that we can provide different abstraction level or different type of abstraction in order to support failure reasonings as different levels. And also, for example, you can support high-level planning reasoning or like low-level execution failures reasoning. And in contrast, in the second project, we actually are trying to build a hierarchy in a top-down fashion, that we're trying to use the top-down task decomposition to support efficient exploration by using this verify and retry mechanism at each of the level. So I think personally, I really feel like this idea of hierarchical representation, although it's not new, it has been there for a very long time, is a very interesting and also practical idea of how we can ground those very structured large language models into our continuous and unstructured physical world, so that potentially they can be a lot more useful for our robots, which need to deal with all this continuous and messy physical environments. And that's the end of my talk, and thank you for listening, and I'm happy to take questions.
Does anyone have any questions?
Hi, great talk. I just want to know, what is the encoding for the robot's capabilities when you're priming the LLM? Like, does it know it's a bimanual or a single manipulator? How is the robot's morphology or the robot's capability, like gripper, etc.?
Are you asking for the first project or the second project? Or both?
More for the first part, maybe.
So actually, for both of the project, we are using very similar robot hardware. It's a robot arm, 6 off, and with a binary close and open.
But is that provided as a prompt? It's converted into text, the joint limits?
I see. Yeah, so the question is that does the robot information is provided as a prompt for the LLM to, for example, generate the plan and the action? That is correct. We do need to provide the information about the robot capability. I think we need to tell them that it's a binary parallel or gripper in the prompt for them to generate reasonable plans. Yeah.
Thanks.
And actually, I will provide even more information because we are collecting the data in simulation. So we actually know the full object state. We also even know the object part information because objects URDF actually is combined with like part, and parts can be like meaningfully labeled. We use that information as well to support the plan generation.
Thank you for your presentation. And I'm kind of curious about the first project you have introduced. So have you ever thought of like predicting explanation of the failure like beforehand it fails? Like, for example, like your grasping pose is unstable, so you may fail like that.
I see. So you're asking whether we can predict the failure before it happened?
Yes. Have you ever like experimented on that?
We didn't experiment on that. I think it's a very interesting idea, but I also can imagine it's really hard because that's requires. So if you already know that it's gonna fail beforehand, then that's probably like we can already build that part into the plan. So I think it requires a whole set of different capability. You need to understand the task, or also understand the robot capability, and also understand the policy itself in order to reason about that. Yeah, so I think that probably requires a lot more than what we have studied here. Yeah.
Thank you.
Okay, if there's no more questions, then let's thank the speaker again.
Thank you.